All right, let's get started. Okay, questions? I was hoping to go over some questions from the assignment, but not everyone has handed it in, so I can't. So that kind of sucks. Okay, circular motion from the review, from the worksheets, whatever you want. Even from the assignment, if I can answer it, I can. Question 3 and 27 from the other review worksheet. What's the other review worksheet? Let me just check to see what I'm talking about here. Let's go to Teams tab. Circular motion. Oh. Circular motion. Okay, so we have two reviews. We have a circular motion review and a gravity review. So I'm assuming that I can't go over the assignment. Okay, so first of all, I'm going to go over 3 and 27 from the, I think it's this one. Is that right, Victoria? Okay. And then I'll go to the circular one. So this experiment was set up between two identical sets of masses. What would the net force of attraction be on one set of the masses? So so like you have this bar hanging from a string, and so if it rotates, that means this one's going that way, that one's going that way. So what is the attraction between one set of masses? So between the little ball on this side and the big ball hanging there. So Fg would equal 6.67 times 10 to the negative 11 times 2 times 25, and then divided by 0.3 squared. That should be the answer. Times 2 times 25 divided by 0.3 squared. 3.7 times 10 to the negative 8, right here. I hope that answers your question. Just respond if it doesn't make sense. 27. Okay. Let me just double check that it is 27. Yeah, okay. A blah, blah, blah rocket initially at surf rests if the rocket's mass does not change. Okay. Because it's saying, okay, so this is a bit of a tricky part here, because there's at rest according to the Earth, but if you were to look at the picture from like this view, the way you're looking at it right now on the paper, it wouldn't be at rest because the Earth would be spinning. Now, this rocket's at the North Pole, which means that it's not actually spinning at all, so its initial velocity is 0. Okay, so that means its EKI is 0, and it has some sort of EPI, which we don't know yet. And then at the top, what maximum altitude will it reach? Well, this is just going to be EPF. And then maximum altitude, which means that the EKF will be 0 as well. Questions like this, where it's asking how much energy would be required to get a satellite into orbit or something like that, they're a little bit tricky because there's kind of two ways you can look at it. There's the way where you have a satellite at the equator, and we put it at the equator because that's where the Earth spins the fastest. And then you give it a certain amount of energy and it enters orbit, and it actually stays in orbit. So it circles the Earth like that. If you think about the work required, work is always going to be a change in energy. Okay, it's straight out just energy. Okay, so that means all of the potential energy, all of the kinetic energy, you have to figure out what all of that stuff is. Okay, so over here, the total energy it has here will be the 1/2 EP. I'm not actually answering the question. I'm just explaining how this works. 1/2 EP. And then here we have EK plus EP. Now the potential energy is relative to some infinite where G is 0, infinite radius where G is 0. But the EK is dependent on how fast the satellite is traveling around the Earth. Well, in order to solve that, you need to go V equals 2 pi r. R would be the radius of the Earth divided by period, which is 24 hours, to find the velocity of the satellite moving around the Earth. Okay. Now, the tricky part about this is you cannot use V equals square root G M over R. Okay, that's the formula we use to find the velocity of something in orbit, but it's not in orbit, right? Something that's just sitting on the surface of the Earth is not in orbit. If you wanted to know, okay, so like if I were to do this for the radius of the Earth, I would get V equals, I think it's something like 7,090 meters per second or something like that. Okay, well, the Earth is not spinning that fast. Okay, it's only going like 400 and something meters per second. This is how fast you would have to throw something on the surface of the Earth in order to keep it in orbit. Okay, on the surface of the Earth. Now, with air resistance and all that stuff, this would have to be much higher. You don't have that problem in space because there is no air. But on the Earth, that's for objects in orbit. Something that starts on the surface of the Earth that isn't in orbit, you have to use this velocity to get the kinetic energy. And then the total work is just a delta E. Now, the other way to look at it, okay, so that's the proper way to do it, to find the actual work done. The other way to look at it is to say, okay, let's ignore the kinetic energy of the object moving around the Earth. And let's just look at the fact that the work we're doing is against gravity. We're trying to escape the Earth's gravity. Okay, so if you do it that way, then all you have to do is work is delta EP. Delta EP. Okay, and people did this on the assignment, and I gave them marks for that. Technically, it's wrong, but it's fine if we're doing that because it's just the EK is not as relevant as the EP because we're working against gravity. So that's why I'm giving you marks for it. Now on the test, I expect you to know now that it has to be total amount of energy. Okay, so that's where the difference is. Okay, so for this one, for this specific example, if we're using 3 times 10 to the 11 joules of work, then the work done is a delta EP, like that. Okay, and so then, oh, this is a tricky question. What I'm going to do is I'm just going to do work equals EPF minus EPI. I'm not going to change it into that because we derived the formula where it was like G M1 M2 times 1 over Ri minus 1 over Rf. I'm not going to do that because the Rf, I want to know the altitude. I don't want to know Rf. Okay, so I'm just going to do it like this. So the work is, well, let's find EPI first. EPI is going to be negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 5.2 times 10 to the 4, and then divided by 6.38 times 10 to the 6, okay, because it's still, the radius is still 6.38 times 10 to the 6. So, I hate typing all these long numbers into a calculator, but it's getting boring. Times 5.2 times 10 to the 4 equals divided by 6.38 times 10 to the 6. Okay, so the EPI is negative 3.25 times 10 to the 12. And so then if our work is 3, come on, Ben. Three times 10 to the 11 equals EPF, which is what we're trying to find, minus negative, so plus 3.25 times 10 to the 12. So we're going to take that 3.25 times 10 to the 12 plus 3 times 10 to the 11. And then we get 3.55 times 10 to the 12 equals, and then EPF. So this is going to be G M M over R, and this is RF, and then we can solve for R. So 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 5.2 times 10 to the 4. That's GMM. And then we're going to divide that by 3.55 times 10 to the 12 to get RF. And so now I have RF is equal to 5.84 times 10 to the 1, 2, 3, 4, 5, 6 meters. But this is orbital radius. This is including the, that's from here to here. Okay, so we need to subtract the radius of the Earth from that, 6.38 times 10 to the 6, to get, I got a negative number. I did something wrong here. Okay. Oh, is it taking EK into the account? It probably is. Okay, so let's say, that's okay. Let's say it's total energy here, but it doesn't even say it's in orbit. Is it in orbit? Okay, let me try something for a sec. What was I going to do? Oh yeah, 3.55 times 10. Okay, that should work. Oops. This is a very poorly worded question. 4. No, that didn't work either. I have no idea what's going on here. One second, just check the chat. Where is it? No, whatever. Okay, don't we have to add H and R? I don't understand. And use that as an... Yeah, that's what I was doing. But the... Okay, just wait. I did 6, right? EKF. Yeah, this is, I don't understand this question. It's okay, at rest on the surface of the Earth. But is it moved why? Okay, maximum. Don't. Yeah, I don't really like this question. It's too confusing. Where it's there's too many assumptions that you have to make. Yeah, I'm just super confused with this. EPI. Maybe I made a mistake in my calculator. That's minus work equals EPF minus EPI. Okay. Oh. I know this is making super entertaining stuff right now. Oh, crap. I don't know how to type this in my calculator. It's too long. 5.84. I got... Maybe it's just... Like, I got this answer, 5.8 times 10 to the 6. What does the answer key say? How do I get to the answer key? What is the answer? Do you guys know the answer? Solutions. Okay, this is 27. Oops. I lost my page. Okay. EPF. So I'm trying to find, yes. Delta EP 2.95. What? EPF. It's EPI plus work. Oh, that's what I did wrong. Oh, I'm so stupid. I was adding these two together. Ugh. 3 times 10 to the 11 minus 3.25 times 10 to the 12. There we go. This is not right at all. This is supposed to be negative 2.95 times 10 to the 12. Stupid mistakes. Okay, so then 6.67 times 10 to the negative 11 times 5.98 times 10 to the 4 times 5.2 times 10 to the 4 divided by that answer. And this should be negative now. Right, yep. And then minus 6.38 times 10 to the 6. Yay, 6.5 times 10 to the 5. There we go. Okay, stupid mistake on my part. Apparently I don't know how to add or subtract. Okay, there you go. That makes more sense. I'm glad I found that out because that would have bugged me. Okay, could you go over number 5? William, that is the circular motion review. So let's go to that one. I forgot what number. Number 5. Okay. Come on. Okay. This is another one of those. This is like the first example we ever did. So I couldn't understand the question itself. Okay, so yeah, these are kind of confusing. So if you have like obviously if you have a mass connected to a string and to a mass like that, like if you just let this go, this mass is going to go that way, this mass is going to go that way, and it's going to accelerate like a pulley system, right? But if you look at the top view, if you spin this fast enough, it will create an orbit. Okay, it's the same thing. Like if you think about the Earth, okay, and if you shoot a gun fast enough, that gun, like the bullet will fall, right? So what we get is normally we get a gun that does this. Okay, the bullet does a parabola and it falls towards the Earth, like that. Okay, but if you shoot it fast enough, it's going to fall like this and keep falling and keep falling and keep falling and eventually get back to where you are. Okay, so if you throw something hard enough, you can create an orbit because the tangential velocity, the velocity that is tangent to the gravity, is big enough that it can cause orbit. It falls fast enough or slow enough. It falls slow enough, slower than its actual tangential speed, that it always falls around the Earth. That's what we're doing here. If you throw this fast enough, the mass will keep going in a circle. Okay, because it has something pulling it towards the center of the circle all the time. Just like this. This gravity is pulling it down towards the center at all times, but it's fast enough that it won't actually fall. It just keeps falling around and around and around. Okay, so that's what we're doing. Yes, so this mass right here is pulling down. So this Fg of it would be capital Mg is causing a tension in the string, and the tension is going throughout the whole string, so that the tension is the Fg, which is causing the Fc. So in this case, Fc would be Mg, like that. And then like when I go mv squared over r equals mg, these aren't the same masses. Okay, that when you do Fc, this m is the thing that is traveling in the circle, that is experiencing the centripetal force. This is the thing that's causing the centripetal force, which is the mass of the other thing. So when I have the Earth like this and a satellite over here, and Fc equals Fg, this mass, mv squared over r, is the mass of the satellite because it's the thing that's actually falling, that's experiencing the Fc. And then Fg will be m, I'm just going to write g like that. The g is not 9.8, but this is the mass of the Earth because it's the thing that's causing the centripetal force. It's creating that centripetal force. Okay. Let me see here. Okay, perfect. Okay, more questions. I don't see any others. I can't answer number 3 from the assignment. Let me see what the assignment is. Where did I post it? I posted it in the Files tab. Let me see what number 3 is. Where did I put it? Oh, there it is. Okay, all I can say about this one is, so every time you have a roller coaster, so let's draw a roller coaster, like you go up a hill and then down a hill like that, okay? At this point of the hill, the free body diagram would look like this, Fg and Fn, okay? And the Fc is going downwards, okay? Because this is the circle right here, okay? And so it put towards the center is downwards. And so you go negative Fc equals Fn minus Fg. And in this case, Fn, you would feel lighter than normal because gravity is going to be stronger than it normally is because, hang on one sec. Gravity is going to be bigger. Yeah, so your gravity doesn't change. This is mg. So in order for centripetal force or the net force to be downwards, this has to be less than gravity. Okay, and that's where you'll feel like those butterflies in your stomach where you're like, ooh, okay, at the top of the hill. And then at the bottom of a hill, the FG is going down and the FN is going up. In this case, FC is going up, FN minus FG. And in order for the net force to be going up, this has to be bigger than FG, which means that what you normally experience, so somebody, in this case, it's 755 newtons. Somebody who normally feels 755 newtons, which you don't feel at all because you're used to it, it doesn't change. So it's just your body becomes accustomed to it. So when that Fn increases, because it has to increase in order to be a centripetal force, you're going to feel way heavier than you actually do. Okay, it's the same thing in an elevator. Okay, this is apparent weight. And so this question is saying that the person seems to weigh at the bottom of a dip. Seem to weigh is Fn. This is apparent weight. Okay, and this is true weight. Okay, so that's how you know what's what. Okay, other questions? I made that roller coaster a vertical circle. What does that mean? It doesn't matter as long as you analyze it at the bottom of the arc. Okay, if there's no more questions, we will start on electrostatics. Okay. Now the reason I'm okay with this is because it's a lot of the same thing. Okay. So, and I'm not going to go through like all this stuff. So if pretty much, okay, summary of this stuff. Electrostatic force, a force that exists between electrically charged objects, okay? And this is, if you think about what's positive, what's negative, okay, they're completely arbitrary. We just say one's positive, one's negative. We don't know what positive or negative means, okay? Protons are positive. Electrons are negative, okay? Hopefully you know that. Because everything around us is created by matter, created up from like, it's made of atoms. Atoms have protons and electrons in them. So if you rub a balloon against your hair, what happens is you can charge that balloon. You can transfer charge or electrons to that balloon, okay? Now this unit is called electrostatics, which means that we're going to have like, it's kind of like equilibrium with charges. But we're going to talk about moving charges as well. So it's kind of a misnomer there. So static means unmoving, charge just means an imbalance. Conductors, this is just review from Science 9, I guess. Conductors allow charges to move. And when we talk about movement of charges, we talk about flow. Okay, it flows down through an object, and insulators hold charges in place. Okay, negative charge electron, positive charge proton. I'm not going to do this. I actually show a demonstration normally that how things charge, but that doesn't matter. Okay, so law of charges, and this again is all review. Okay, opposite charges attract. Okay, that should be obvious. Like charges repel. Oops. Okay, and then the last one doesn't really apply to us, but it's neutral objects attract charged objects. Okay, this is if you rub a balloon against your hair, you'll charge it. If you stick it to a wall, it'll stick to that neutral wall. Okay, and the reason behind that is you have this balloon that's negative, you have this wall that's positive and negative. The negatives in the wall will move away from the balloon, leaving the outside of the wall positive. And so we call this movement of charges polarizing. Oops. So it'll polarize the wall, which means that we're just making the inside negative, the outside positive. And every time you have two areas that are different, we can call it poles. Okay, think of a magnet, north-south pole. Now we have a positive, negative end. So positive one side, negative the other. So yeah. And then examples, again, I show this demonstration, balloon, pop can, all that stuff. Hopefully your teachers have showed you that. The vinyl ruler in the water tap. So if you take a paper towel and rub a vinyl ruler and put it beside a stream of water going down from a tap, it'll bend the tap. It's really cool. You can do it at home. Okay, so now the important part, Coulomb's law. So if we have like a positive charge and a negative charge, okay, these will attract, okay, and they'll move, they will accelerate, which means there has to be an electrostatic force here. Okay, so Fe is electrostatic force. And the same way like this, if you have a positive and a positive, well, this one's going to go that way and that one's going to go that way. What's going to cause them to go that way? Electrostatic force, okay, Fe. Now, notice how in both cases there are two charges. And remember that we just finished a unit called gravity where we had a mass and another mass. They attract each other like that due to this formula right here, Gm1 m2 over r squared. Okay, that was the formula for gravity. Well, the electrostatic force, and I'll keep that in view, is Fe equals K Q1 Q2 over r squared. Okay, Q1 is the charge number 1. Q2 is charge number 2. Okay, and these are measured in coulombs. Coulombs. Okay, charge is measured in coulombs. R is the distance between the charges. And we don't really have to say the distance between their centers because we're talking about protons and electrons here. They don't really have centers, right? They're like an electron is pretty much nothing. It's just a weird lepton thing. So even if we did the distance between their centers, it's going to be so small that it's not going to make a difference. And then K, so if you look at gravity, so if you think about Fg equals Gm1 m2 over r squared, this G here is the gravitational constant. So for electrostatics, we have something called Coulomb's constant. Okay, and its value is 9 times 10 to the 9 newtons meters squared per coulomb squared. Okay. The biggest difference here, and this is K equals, the biggest difference is that electrostatic forces are much stronger than gravitational forces. And the reason is because K is much bigger than G. Okay, 9 times 10 to the 9 is a way bigger value than 6.67 times 10 to the negative 11. So it's way bigger. Now, in terms of, so technically, like if I had a proton and I fixed it right here, fixed in place, so it's not allowed to move, and I had another proton right here, technically the free body diagram of this would be this, where I have Fe going this way and Fg going this way. Okay, because it's two masses, a proton and a proton, two masses, there should be an Fg here. Okay, but the Fg, let me just calculate this for a quick sec. So 6.67 times 10 to the negative 11 times the mass of a proton, which is, crap, 1.67 times 10 to the negative 27? I don't remember the value. Let me double check this. Again, it's been a while. Okay, mass of proton. Oh, I was right. 1.6 times 10 to the negative 27. And then times 1.6 times, okay, because it's mass times mass. And then divide it by, let's say this is 0.001 meters. Okay, so like 0.1 centimeters? Whatever, it's really, really small, 0.001 squared. The value of the Fg between these two protons is 1.86 times 10 to the negative 58 newtons. Okay? And the value of the Fe is going to be much, much bigger. And so the Fg that exists between these things is so small that we just ignore it. Okay? There is no force of gravity existing between protons. Okay? It's way, way, way too small. Okay. Some calculators would just display 0 here, right? It's a very, very small number. Okay, very important distinction between gravity and electrostatic. Gravity always attracts, where electrostatic forces can attract or repel. Okay. Now, when solving for electrostatic forces, we will not, I don't know what this is supposed to be. I don't know what's okay. So I'm going to get rid of this. We will define, that not is throwing me off. So when solving for electrostatic forces, we will define direction based on attraction or repulsion. Yeah, that's what this is. No, we'll get rid of that. Okay. So what I mean by that is if I have like the example I just showed you, let's say this is fixed. Okay, if I have a proton on this side and an electron on this side that aren't fixed, this proton will go that way and this electron will go that way. Okay, I'm defining my directions based off of which way they're going to go. Okay, the proton will go away from the other proton and then the electron will go towards it. Okay. Okay, so let's do some examples. I'm just going to do this one real quick. So 6.67 times 10 to the negative 11 times 85 squared divided by 1. The force of gravity between these two students is 4.8 times 10 to the negative 7 newtons. Okay, that's really, really small. Okay, so now let's say the two students each have a charge of not a very big charge. Okay, it's 0.002 coulombs. The electrostatic force that exists between them will be K Q1 Q2 over R squared. So this is going to be 9 times 10 to the 9 times 2.0 times 10 to the negative 3. And because they have the same charge, we can just write squared over, and then they're 1 meter apart, so 1 squared. So 9 times 10 to the 9 times 2.0 times 10 to the negative 3 squared. And so this will be, 3.6 times 10 to the 4 newtons. Okay, so you can see how electrostatic forces are a lot bigger than gravitational forces. Now, the reason why you don't stick to people when you sit beside them is because your charge is much smaller than this. Okay, so this is a small charge, but your overall charge is much smaller than this. And keep in mind that yeah, so it's not gonna, you're not gonna all of a sudden stick to things just because you get a charge. Okay, so let's look at this one. So we have, oh, I know what this is supposed to be. When solving for electrostatic forces, notice how because we have, let me put this, don't use positive or negative sign of charge. That's what it's supposed to be, okay? Because if you have a proton and an electron, then technically in this equation you would go FeQ and then positive Q, or sorry, K times positive Q times negative Q, but this will throw off which direction this is supposed to be. So because this is a vector and the positive negative sign of the charge it's not really anything to do with vectors, okay? You can't put in positive or negative. You just put in the absolute value of the charge into the formula all the time, okay? Okay, so 2-point charges of 1.8 times 10 to the 6. Okay, hang on. What if two objects' charge is negative and positive? How do we calculate? I'll get to that in a sec. That'll be explained in number 3. So 2-point charges of 1.8 times 10 to the negative 6 and 2.4 times 10 to the negative 6 produce a force of blah, blah, blah. So what we sort of do in this case, so this is positive and this is positive, which means that we have positive, positive. Okay, now what we normally do is we fix one of the charges. It doesn't really matter which one it is, but instead of both moving, we kind of fix one. Now there are examples where they both move. Those are really hard examples, okay? But it doesn't really matter, okay? Because if you put two protons like this at a distance apart r, the initial force that they're going to experience will be the exact same thing on both. So it doesn't matter which one you analyze. It's just we're finding the value of the force, okay? So Fe equals KQ1, Q2 over r squared. And we already have the force, we're trying to find the radius. So 2.2 times 10 to the negative 3 equals 9 times 10 to the 9 times 1.8 times 10 to the negative 6 times 2.4 times 10 to the negative 6 divided by r squared. Okay, so then we're going to go 9 times 10 to the 9 times 1.8 times 10 to the negative 6 times 2.4 times 10 to the negative 6. And then divide that by 2.2 times 10 to the negative 3, and then square root it, and we get 4.2 meters. Okay, that's your final answer for radius. Okay, let's get into a little bit harder question. Now, I'm going to say when, right now it says times 10 to the negative 6 coulombs. Eventually we're going to get to the point where it just says 1.7 microcoulombs, because micro is times 10 to the negative 6 anyways. So it's the same thing, okay? Okay, so 1.7 times 10 to the 6, I want to say micro now. 1.7 microcoulomb is placed 20 millimeters from a charge of 2.5. So this is 20 millimeters. I'm going to put this into meters already. So 0.02 meters. Does that make sense? 1, 2, I'm dividing? Well, I'm second guessing myself now. Yeah, that's good. And 3.5 times 10 to the negative 2 meters from this charge. So that means that this distance right here is 3.5 times 10 to the negative 2. I don't know why I'm doing this. 0.035, that's way easier, meters from that charge. And this is negative, this is positive, okay? we want to know the net force on the 1.7 microcoulomb charge. So what we're doing is we're fixing this charge and we're fixing this charge. Okay, assume those two are in the same position. They can't move according to each other. The only one we care about is this one. Okay, if this one, what is the force experienced by those two? And we could fix all three and just say, okay, if you were to let go of one, which way would it go? Okay, so what we have here is this positive charge is going to be repelled by this positive charge, which means that we're going to have a force going that way. We're going to call it Fe1. And this negative charge here is going to attract this positive charge, so we're going to call that Fe2. The net force acting on this is going to be Fe2 minus Fe1. Okay, and then all we have to do is plug in the values. So here we have, and this is where my positive negatives come in, okay? I'm defining Fe2 as positive and Fe1 as negative, so I don't want to add in any more negatives or positives. Okay, well, I want to add in the positives. I don't want to add in any more negatives, okay, because I've already defined direction. I don't need to do it again. I don't need to screw that up. Okay, so Fe2 is going to be 9 times 10 to the 9 times 1.7 times 10 to the negative 6 times, well, I almost put a negative in there, 2 times 10 to the negative 6, and then divided by its radius, 0.035 squared. And then minus 9 times 10 to the 9. Yeah, like you can factor some things out of here, but I'm just going to do it like this. And then times its charge, 10 to the negative 6, and then divided by its radius, 0.02 squared. Okay, now not only is the middle charge bigger, it's also closer, which is why I kind of drew Fe1 bigger than Fe2, because I know that it's going to be stronger. Okay, not only is it a bigger charge, it's also closer. And Fe is affected by both. The bigger charge and the closer it is, the bigger the Fe will be. Okay, so now we can go 9 times 10 to the 9 times 1.7 times 10 to the negative 6 times 2 times 10 to the negative 6 divided by 0.035 squared. This is 24.98, and then minus 9 times 10 to the 9 times 1.7 times 10 to the negative 6 times 2.5 times 10 to the negative 6 divided by 0.02 squared. This is 95.63, and so we get 24.98 minus 95.63, and the F net is negative 70.6 newtons. Okay, notice how this is left. It's going to the left. How the meter is 0.35. It should be 0.035. Right here. Times 10 to the negative 2, so we're going 1, 2, 0.035. I hope I didn't make a mistake there. I don't think I did. Okay. Any questions about that? Any other questions? Does it matter which way the Fe1 and Fe2? No, I just randomly made this one Fe1 and that one Fe2. Okay, the numbers I give them are totally arbitrary. Doesn't matter which one's which. I'm just labeling it 1, 2 so that I know which way they go. You don't even have to label them 1, 2. I just find it easier if I start labeling things. If I have more than one of the same force, yeah, I like to define which one goes where. Let me show you this part of the worksheet. I don't know which part to share. I guess I'll share this part. Okay, so did I say worksheet? Formula sheet. If you go to the Files tab in our formula sheet, right here, the you'll notice that there is no real like electrostatics heading here until you get to the third page. So this is the electrostatics right here. Now, we're going to eventually be introduced to all these equations and understand how they all work. But the first one we just did is Fe. Okay, we just talked about the electrostatic force. Now, if you look at, so I give you the formula. We've already talked about this formula here. There's a column that says units, and then there's a column that says vector or scalar. This is a force, so obviously it's a vector. And then over here it says absolute value or use negative signs, okay? What this means is, notice how there's a bunch of Q's here. So Q, 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 like that's all charge. Because charges can be positive or negative, sometimes you have to use the positives and the negatives, sometimes you don't. So every time it's a vector, so the first two, electric field and electrostatic force, you have to use absolute value. So even if it's a negative charge, you have to plug it in as positive into your formula, okay? Because it's a vector, it's going to screw up your directions if you don't, okay? When we start getting into energy, excuse me, you're going to have to start using positives and negatives because that's going to define which, like whether we need an input of energy or an output of energy, okay? Kind of like when we talked about work and stuff like that. So this is the chart you're going to be using, and if you understand how to use this chart, it becomes really, really easy. So for now, all you need to know is that when you plug in the value of charge, value of Q, do not use negative signs, okay? Even if it's a negative charge, just plug it in as positive. Okay, your directions are defined based on which way your forces go. Very, very important. Okay, now the reason why I don't mind doing this lesson is because it's the exact same thing as gravity. You're using pretty much the exact same formula. Okay, so it's not anything new. And even if we did lesson 2, like it's the exact same thing as acceleration due to gravity. So I'm not too worried about that. So in terms of the rest of the day, please keep working on the review for circular motion. I'm not quite sure if I want to do lesson 2 tomorrow or not. I want to give you guys enough time to do the test. And it's not like I've given up on electromagnetism now, so it's not like we need to go super, super fast. I don't want to have too much time at the end, although that wouldn't be a bad thing. So I'll have to just play it by ear to figure out what's going on with that. But again, the big thing is your test tomorrow for circular motion. So that's what you should be focusing on. Any other questions?
Could you answer my question that I sent in the chat?
In the chat?
Yeah, I mean, like not in the chat. I mean in the 1-1 like meeting stuff. Like I asked for the assignment homework that we have to do.
Yeah.
That was due yesterday, but I couldn't figure out the 11th question.
The example from the notes? Oh, okay, wait.
Yeah, like I cannot understand why the radius is 6.38 times 10 square 6.
Okay, so let me find that example in the notes. Oops.
Yeah.
And that's a good question. Okay, so that was circular motion notes. Get out of here. Okay, and that was this question right here. Okay, so if you think about this question, I shouldn't have done that. Come on. Okay, so an asteroid falls towards the Earth from really, really far away. So you have this asteroid that's way out here and the Earth right here, okay? and this is where G equals 0. The asteroid is coming towards, and it's going to hit the Earth. So its initial position, Ri, is infinity. Okay, it's super far away. The final position is going to be the distance between the centers.
Yeah.
Okay, now obviously the asteroid is not going to be like the center is not going to hit the Earth. Well, it might, but so there's some sort of radius here on the asteroid, but because the asteroid's hitting the Earth, we don't really care too much about that radius. So it's not like you have to add these two radii together. Okay, when the asteroid hits, it's going to destroy the Earth and there won't be a radius anymore. So when we do questions like this, we just call the final radius, because it's going to be on the surface of the Earth when it hits, 6.38 times 10 to the 6. Because that's this right here. That's the radius of the Earth.
Oh, I was confusing, like every example uses this radius, and
Yeah.
I think
it's
from any formula sheet. So right.
It's on the formula sheet. It says radius of Earth, 6.38 times 10 to the 6.
Oh.
Yeah.
All right. Thank you.
Yeah. Okay. Any other questions? Okay. Those of you who have not finished the circuit motion assignment, please do so. Hand it in as soon as possible. Otherwise, I will see you guys tomorrow for the test. And any questions, just message me. I'm around all day, so I will be able to answer questions most likely. So have a great day.